today we are doing limits at infinity. So limits as x approaches positive infinity, or limits as x approaches negative infinity. So let's start with some basic ones. The limit as x approaches infinity of 1 over x. So let's plug in some x values into our function and graph it. So if x is 1, then y is 1 over 1, which is 1. If x is 2, then y is 1/2. If x is 3, then y is 1/3. If x is 4, then y is 1/4. So what if we kind of reversed it? What if x was -1? Then y would be -1 over 1. -2 would be -1/2. -3 would be -1/3. So on and so forth. So if we were to go plot this, we would point at 1, 1, point at 2, 1/2, a point at 3, 1/3. What if we plugged in like 1/2? Like x is 1/2. Then it would be 1 over 1/2, which would be 2. So at 1/2 it starts going up. So what's happening here is the function looks like this. Because x cannot be 0. At 0 I have a vertical asymptote because I can't have 0 in my denominator. And then over here I have -1, -1, I have -2, -1/2, -3, -1/3. So the same thing is kind of happening here. So the limit as x approaches infinity, so as x goes this way, what is y approaching? Well, you notice my fractions are getting smaller and smaller and smaller. They're approaching 0. They're not actually ever going to hit 0. I have a horizontal asymptote there, but my y values are getting closer and closer and closer to 0. So as x approaches infinity, y approaches 0. So my limit as x approaches infinity is 0. As x approaches negative infinity, so as I go this way, same thing's happening. My functions are getting, or my y values are getting closer and closer and closer to that x-axis. So my y values are also approaching 0. Let's do another one. The limit as x approaches infinity of 1 over x squared. So let's plug in some values, make a t-chart. If I plug in x is 1, I get 1 over 1 squared, which is 1. If I plug in x is 2, I get 1 over 2 squared, which is 1/4. If I plug in 3, I get 1/9. If I plug in -1, I get 1 over -1 squared, which is still +1. If I plug in -2, I get 1 over -2 squared, which is +1/4. If I plug in -3, I get 1 over -3 squared, which is +1/9. So at 1, at 2, I'm at 1/4. At 3, I'm at 1/9. And if I were to plug in like 1/2, that would be 1 over 1/2 squared, which is 1 over 1/4, which is 4. So at 1/2, I'm all the way up at 4. And over here, I have -1, 1, -2, 1/4, -3, 1/9, and the same situation's happening. So as x approaches infinity, positive infinity, my y values are getting closer and closer and closer to that x-axis. My y values are approaching 0. My fractions are getting smaller and smaller and smaller. They're never actually going to hit 0, but they're going to get really close. So the limit as x approaches positive infinity is 0. And same thing, the limit as x approaches negative infinity, my y values are getting closer and closer and closer to 0, getting closer and closer and closer to that x-axis. So the limit is 0 as well. So if you notice, all of these limits were 0. So there is a rule. So if R is a positive rational number, and C is any real number. Sorry, my handwriting is struggling today. Then the limit as x approaches infinity of c over x to the r is going to be equal to 0, always. And the limit as x approaches infinity of negative infinity of c over x to the r is also 0. So if you notice, in these two examples, my c was 1, my r was, in this one, r was 1, the exponent was 1. In here, this example, the exponent was 2, r was 2. And all those limits were 0. Okay, sometimes your equation is not going to be quite so simple, so it won't be quite so easy to just tell, oh, that limit is going to be 0. So how do you determine the infinite limit of a rational radical function? So rational function is just something that has a denominator. Radical function has the square root. So how do you determine the infinite limit of something that's a little bit more complicated than those problems we just saw? So the first thing you're going to do is divide each term in your numerator and your denominator by the highest power of x that occurs in the denominator. So basically, you're going to pick the highest power out of your denominator, whatever's the highest power in the denominator, and divide everything in the numerator and the denominator by that highest power of x, which will make more sense in just a second. And then the second thing is you're going to evaluate the limit using our basic limit laws, so all the things we know about limits from the past. And that special property of infinite limits that we just learned. So we're going to divide everything in the numerator and the denominator by whatever the highest power of x is that's in our denominator. And then, once we do that, then we can use our normal limit laws and that special rule that we just learned about how when x approaches infinity or negative infinity, when you have c over x to the r, it's always going to be 0. All right, so here's an example of a rational function, and we are trying to take an infinite limit of this. So it doesn't look like c over x to the r. It's a little bit more complicated. So the first step says divide each term in the numerator and the denominator, by the highest power of x that occurs in the denominator. So the highest power of x that occurs in my denominator is x to the second power. So I'm going to divide the numerator, everything in the numerator by x to the second power. I'm going to divide everything in the denominator by x to the second power. So dividing by x squared is the same thing as multiplying by 1 over x squared. So I'm going to multiply by 1 over x squared in the numerator, and I'm going to multiply everything by 1 over x squared in my denominator. So I'm going to have to distribute those. So now I have the limit as x approaches infinity of 4x over x squared plus 1 over x squared, and then 5x squared over x squared minus 15 over x squared. So now I can reduce the limit as x approaches infinity. This is 4 over x plus 1 over x squared over, the x squared cancels out, 5 plus, minus 15 over x squared. So now all three of these things look like what we just talked about for our special property of infinite limits. I have a real number in my numerator, and I'm raising x to a positive rational number as my exponent. So the limit as x approaches infinity of 4 over x is just 0. The limit as x approaches infinity of 1 over x squared is also 0. The limit as x approaches infinity of 5, remember when you take the limit of a constant number, it's just the constant number. And then minus the limit as x approaches infinity of 15 over x squared is also just 0. So I'm left with a 0 over 5. Remember, I cannot have 0 in my denominator. It's okay to have 0 in my numerator. This is fine. I can't have 0 in my denominator, so that's why it's super important that I have a 5 chilling in my denominator. So 0 over 5 is just 0. This is one of those problems that you have to show the work. You need to show this step, all of this stuff, showing how you get 0, 0, 5, and 0. You can't just say, oh, I know this is going to be 0. You have to show the work, or you're not going to get any credit. You must show work.